So today, what are we going to do? For the sake of those who did not attend with us and possibly did not watch the lecture that I already posted in the folder, we started already chapter number 12, which is about lubrication and journal bearings. And we said that in simple terms, journal bearings are basically those elements which consist of a journal, which is this, basically it's the shaft. And then there is a bearing element surrounding the shaft. And in between, we have a lubricant. Very simple. No trace, like the anti-friction bearing, the rolling bearing trace, and then a separator, and then there are balls or cylinders, nothing. Just a uniform diameter, and then a gap in between. There is an oil, lubricant filled, and that's it. So we said that this kind of bearings are very common in the industry, and we talked about different type of lubrications for one sake, because we said that in these bearings you have nothing except like actually even the bearing element itself, although it is made from some material, but if you do not necessarily have a contact, between the two, then the whole thing is coming to the journal, which is the shaft, the bearing, which is just a sleeve, something, and then the fluid in between. So the lubricant makes a big deal out of these. And to do that, what did we do? I mean, now we are engineers and we are in a university. So in the university, we always try to understand the basics, the fundamentals, and then dive, or build on those fundamentals to understand this practical problem. In the contrary to what many people believe, unfortunately, that this is just for books and it doesn't mean anything. Okay. Now, what do we have here, just for the sake of clarity, is that I'm going to go over this quickly, as I said, but I have to go over it. So what do we have over here is a simple problem with a stationary plate, if you want to think about it, here, and a movable plate, a platform A, moving with a velocity. This velocity is capital U, and this motion is driven by F, the force. Now, if you imagine that we are having, this is the journal, okay? Then this is the fluid, which is the lubricant. And this is the bearing, okay, holding on. So basically, what are we doing here? We are just going to take a little slice of this. And again, in a simple theoretical way, we assume that the curvature here, that this is straight, and then the curvature here is straight. And actually the whole journal, which is around, we just took it as a little strip. And then what do? We say, okay, what happens when you have the fluid in right here, and then you have this one rotating, which is moving? Well, the first thing first is that, as you understood from fluid mechanics, that we think of the fluid. Let me just fix this. I think it is more toward the window. So we think of the fluid as a duck of card, like on top of each other. Now, if the bottom plate is fixed, then essentially this bottom layer over here of the fluid is not going to have a single value of a velocity. It doesn't have a velocity. It must be stationary. And the top one over there will have the velocity capital U. What is in between is the question. Now, you can imagine that as you move on from a zero velocity to a maximum velocity, you can go in a straight line. Let's focus on the straight line, because there is a chance that the change of the velocity du over dy as you move up, the change is not linear. So you may end up with a change like this or a change like this. We don't like nonlinearity, right? So let's not speak about it. Let's assume that this relation is linear, okay? And somebody might ask, why would the fluid be sheared off with this line? Why not this line? Why not this line? Why not that line? Why not? So the idea here is very simple. This slope characterizes something here. And just before we talk about what is this slope, I want to tell you that here, the height here, h, is the maximum thickness, is the gap between the journal and the bearing below. The y is just a distance. It can be 0, it can be something in between, it can be even h. And then mu is the viscosity, which will come soon in the next slide. The viscosity, ya shabab, is measured by different unit, a little bit confusing sometimes. In IPS system, which is inch, pound, and second, it is pound force second inch square. This pound force second inch square is abbreviated, just like a Newton meter, which is Pascal, is abbreviated as Ren from the scientist Reynold, okay? And in SI unit, it is Pascal second. And in centimeter gram S unit, it is called poise. And if you say centipoise, it is 1/100th of a poise. Okay? I think you will learn how to deal with these units. Now, what happened? Let's go back to our discussion. Is that if we look at the shear stress in the fluid is sitting, and then there is a force trying to shear it off. Then if we calculate the surface area with that force, we will calculate the stress. Now, without discussion, that stress, okay, can be related to proportionally to the rate of change of the velocity with y. This is the velocity, this is y, small u over y. Now that rate of change will is basically how this slope is changing, right? It's like how fast. What is the rate of change of the velocity as you move up? And as we all know, that usually whenever you have a proportionality between two quantities and you replace that proportionality with an equality, you should have a constant. Now, if you're lucky, that constant will be a physical quantity. Yeah, a physical quantity. Like F is a proportional to the mass, the inertia. I'm sorry, F is proportional, to the acceleration, okay? And it turns out that the proportionality constant is the mass, correct? Now, what happens? It turns out that this proportionality constant is mu, which is the viscosity. Now, if we still assume, of course, this slope, okay, is changing due to the change in the characteristic of the fluid, right? So if we assume that this slope will be constant or linear, then the du over dy can be measured as u divided by h, which will give you this equation. Tau equals to mu u over h. Now, if you assume that the rate of shear is constant, then this fluid is said to be a Newtonian fluid. A Newtonian. Okay. Okay. Now, and then we said that if you, so now we talked about viscosity, and it is very important for the bearing. Now, if we check this graph, which will tell us that this is the change in the absolute viscosity, which is the dynamic viscosity, in Ren, which is the bound, second per inch square. With temperature, we see that most fluids loses their viscosity as you increase their temperature. Okay, this is something will turn out to be important, and we'll discuss it later. Now, just for the record, if you want to change from one unit to another, here if the viscosity is expressed in centipoise, then it is designated by Z. And here we have a micropascal second is equals to 10 to the power minus 3 centipoise, and this is going to convert this. So this is the conversion between a centipoise and the Pascal second. And here we have it between Ren and centipoise, and here between a micropascal and then a microren. Okay, just for the record, a microren is given here. Like you see, we are putting mu prime. So mu prime is actually mu. Mu is actually equals to mu prime divided by 10 to the power 6. Okay. Now, what are we interested in next is an equation which was derived by Petrov. This equation will not be used a lot next. Okay. But Petrov equation is a fundamental equation for finding the relation between the friction, which is very important parameter. I mean, look, the whole thing is about two surfaces moving. One of them is moving with respect to the other, and there is a fluid in between. And the whole story is that this fluid is viscous, it has a friction, and you want to understand the characteristic of this while these huge turbines are moving. I mean, if you think about it for a second, it's very interesting. You have a turbine, the rotor of the turbine can weigh tons, thousands of kilograms, and then it's sitting comfortably on this journal, on this journal bearing, okay, with a little tiny thin film. And that's it. It does the job. No friction between metal to metal. So what are we going to do during this class and the next is we are going to state or develop the fundamental equations in relation about what happened in that tiny little itch. What happened? Well, what is the pressure? What is the friction? What is the RPM? What is the viscosity? Negligible. Nobody would ever believe that anybody would pay attention to that little tiny microfilm of fluid. But that's how we do things. So Petrov started by taking an concentric shaft, and in reality, by doing his experiment and analysis, he was able to establish an equation. The equation itself has a few dimensionless parameters. And those dimensionless parameters were found to be very useful. for design and analysis of journal bearing. So how did it start? As you see, we have a journal over here, and we have a bushing, the bearing, basically place. Then the fluid here, okay? The fluid is there, all right? Now, what did we do? We started by saying, okay, journal bearing, they rotate. So there is an RPM. So if we assume that the RPM of the shaft or the journal is measured in revolution per second, so how many revolution per second, then the velocity, or in another word, the surface velocity, the velocity at the surface. Now, we all know what is the relation between the velocity of a cylindrical part. This is omega, and this is V, and this one is R. V is equal to omega R, correct? So if I say that the velocity is U, and then I have omega is in radian per second. So I multiply 2 by, which is in radian, divided by a revolution. That's 2 pi equals to 1 revolution. And then I multiplied by what? N. So I need to multiply N, which is in revolution. So N is in revolution multiplied by R. So the revolution is gone. I ended up with 2 pi NR, and this is it. 2 pi NR is the velocity at the surface. Now, if I know that velocity, I can go back to the shear equation and say, oh, shear is equal to mu, the viscosity multiplied by U divided by H. Now, as per the figure we have here, Petrov decided that this little gap where the thin film exists is called C. That doesn't make any problem for us. So okay, so I'm gonna replace H with C. I'm gonna replace U with 2 pi NR, and I'm gonna just plug the viscosity here over there together. Now I got the shear equation saying that I have the shear equals to 2 pi R mu N divided by C. Now remember, the more we have variables that are related to the design parameter, like RPM, pressure, load, viscosity, the better it becomes for us, because engineers want to deal with these numbers. Give me RPM, give me what is the clearance, and that's it. They want to find numbers out of these. Okay, so we move on. Now the question is, if you have this bearing rotating, then there is a torque, there is a friction, and then there is a torque. So the torque, as we know, torque is equal to F multiplied by R. Correct? The force by radius. And now we are looking into a torque equation, which is as simple as this. This is the center, this is R, and this is the force. Right? Now, but we haven't spoken about forces, right? We know stress. So we know that tau equals to F over A. And if I want to know the force, I can say that the force is equal to tau A. So this is the force. I multiply it by R, and I get the torque. That's really good. Why? Because when I look here, I would see that this is tau A, which is the force. This is the radius. Now, all what I need to do is to go to the shear equation and bring it right there. This is the shear equation. Correct? Now, what is the area? Yeah? So the area is going to be equal to the circumference. This is like a surface area. It's going to be 2 pi R, which is the circumference, multiplied by the length. The length here is the depth, to get all of the surface area around this. Correct? So this is the area, 2 pi R multiplied by L. And this is L, ya shabab. Then multiplied by R. Because all of this is what? Is F. So we multiply it by R and we get this equation. Now, just put it aside. This is the torque equation, right? Now, if we look into the frictional torque, okay, then the frictional torque supposed to be equal to what, ya shabab? Something, I mean, look, there is a weight which is being carried by the journal, right? Makes sense. So if I look at that weight, okay, and then I multiply it by the friction, then this is the friction force. Because what happened is about the friction force is the normal. It's, do you remember? It is mu n, normal force. Now, this is a normal load, W. So the normal load down will be W. So if I multiply that by the coefficient of friction, I get WF. If I multiply this by W. So this is WF. And if I want to get what is the friction torque, so it is the torque generated because of the friction, the frictional torque, then I need to multiply it by R, right? So in here, look, I have the friction multiplied by W multiplied by R to get the frictional torque. The question is, while F is the friction, okay, which by the way is unknown, and R is this radius, the distance from the center of the journal to the surface, I don't know what is W. W, ya shabab, is the weight, or I mean the load, and although I can measure it, but I can express that load in a better parameter. And this is something you will see later. So in reality, we can think about the pressure. You know, you can put a gauge and measure the pressure. So you can think about the pressure generated by that weight, by that W. So that pressure, which is equals to F over A, pressure is equals to force over area. So what are we going to do? We are going to look at this W as a load, applying. So I'm going to get the pressure by taking that weight, dividing it with respect to the projected area. The projected area is this 2R. So if this is 1R, this is another R. So these are 2 R's. And then when I multiply them by the length L, I get the projected area. So here I am getting the pressure as the force by the projected area. So in another word, W is equal to what? P 2RL. Yeah, and this is why we put it here. So look, this is now the friction. I mean, not the friction. This is the torque. The frictional torque is equals to this. Now, using these two relations, this is what Petrov did. He came up with the coefficient of a friction equation. Now look, inside this equation, there are very important numbers. So F is equals to 2 pi square mu n divided by P multiplied by R over C. Now, this ratio, as written down, this ratio is very important. It actually has a name. It is the bearing characteristic number. And this ratio over here is called the radial clearance ratio. And if you look at them, it's R the radius of the journal. It's C, the gap between the journal and the bearing. So it's basically telling you how much is the fluid in there. And the mu has the viscosity, N has the RPM, and B has the pressure. Yeah? Remember, in design, if you want to calculate the pressure, you just put a pressure gauge, which is very simple. Pressure gauge doesn't even need power, electronics. If you want to measure the force, you need a force gauge where you have to have some electronics, and then it will tell you how much. You have seen it in machine in manufacturing process. They put the sensors, and then you have to connect them to some electronics, and then you get the force in a Newton. So a pressure is very simple. You can imagine that in the journal bearing, you just put put a pressure gauge, which are cheap. You can find them anywhere. The RPM is a very standard term. You go to any industry, nobody in the industry doesn't know what is the RPM of this pump, what is the RPM of this turbine. Nobody. Oh, this is like their name. The viscosity is basically what is the fluid. When you say I'm putting this oil, which is grade 1202, whatever, that basically its name reflects one property, which is viscosity. R is the radius, and C, as I said. So these are very important numbers, and this is why Petrov equation deserve to go, to deserve the attention that we are giving it to it. Now, the bearing characteristic number, or as it is known as the Sommerfeld number, is defined by S, which is equal to R divided by C square multiplied. It's just basically this radial clearance ratio square multiplied by other ratio. That's where the importance comes for these. So the whole derivation here is to come up to Petrov equation and tell you, listen, this Petrov equation has 2 pi squared. This is just 2 constant. And then we have these ratios, which are very important for design and analysis of journal bearings. Now, if we just for the sake of, if we multiply this equation by R over C, we will get this relation, which, by the way, this one is the same as this one. So you can see here, this is the characteristic number coming up again, which is equal to F R over C. All of them are basically very important numbers. So this is an interesting relation. Now, what is important? Now, we know the friction. We're going to go step by step, Shabab. So in next class is going to be a little bit heavy in fluid mechanics, but what we are going to go step by step. So this section 12.4, which is about stable lubrication. Now, when Petrov established his equation, okay, there were 2 brothers made a plot, which is very famous, known as McKee brothers plot. So what they did, they made an experiment to have the coefficient of friction in Petrov, which is on the left-hand side, and mu NP, right? You remember this ratio, which has the RPM, the viscosity, and the pressure on the other side, on the x-axis. And they ran the experiment, and they realized that there is a curve, there is a trend, which relate these two, this characteristic number with F. And as you see, the curve is very clear, climbing like up over here, going down, and then moving up like that. Now, it's very hard to start the discussion. So let me tell you. On the right-hand side, we have what is known as thick film, and between 2 parentheses, stable. On the left side, we have a thin film, and it is unstable. So what is the story? Well, on the right-hand side, which is A, over here, we call it, this is region A. And of course, the right-hand side starts from here. I'm gonna tell you what is this number. Definitely, if there is a stable region and there is unstable region, then the line that separates these two regions will always be of an importance. The number there can guide us, can tell us where are we. So we will talk about that number later. But if we are in region A, then we are at this situation. Look, in here, this blue, dark blue color indicates the boundary film, which is very close to the surface of the bearing and the journal. And of course, the surfaces are shown here, rough. You would never be able to make them straight, no matter how much. And the below surface will have the boundary, fluid sticking to it. And then in between, we have this thick layer of light blue color, which indicate comfortably that there is a gap between the two metals. And as things flow, there is no metal to metal touching, no contact, which is very good. So this is the case of having a thick film. Now, what is the story over here is the following, is that if you maintain this, of course, to maintain this, you need to make the condition right to be on the right region. Is that true? So you need to make sure that mu n divided by P is more than this number. So go and do it. I will increase the decrease the pressure, or increase the viscosity, increase the RPM, do the analysis so that you become on the right-hand side. Now, when you are on the right-hand side, why do we call this a stable condition? Because in a simple term, convincing analysis, it says, look down, I made it, it is written in your book, but I made it in a symbolic form. It says that if for any reason there was an increase in the temperature while you are here, there is an increase in the temperature, then viscosity will drop. We all know this. We showed you the curve. So the viscosity will drop. Arrow down for viscosity. Next, the viscosity drop. We all know that the more viscous the fluid, the more friction it generates. So if you drop the viscosity, the heat generated by the fluid, the lubricant, will drop. In another word, the temperature will not increase. It may even drop, which means that you increase the temperature and the process itself ending dropping it or stabilizing it. And that's it. That's what you want. Everything is running. There is a little increase, there is a little decrease. They decrease and increase, and then they equal each other. And then that's why it's very stable. Now you will see later in the next one that no, something changed, the other one changed, and then things get bigger. This is when it gets worse. Okay, so in the B region over here somewhere, okay, you have this partial lubrication mixed between, if you remember from the last class, we talked about this boundary. And we said that in boundary lubrication, you may end up having a thickness of molecules, measures in molecules. Look at it. The blue, the dark blue is very little, right? Now, it's very clear, and the fluid in between, which is very important, is not thick. It's very little tiny layer there. So this is now your life, the survival of the machine, the integrity of it depends on how much this boundary layer will hold. And if you remember, we said that this depends, it's proven to be dependent mostly on the chemical composition now. So if we go, sorry, Shabab. Now, what if we go to C. Look at C. C is very tough. You can see that the fluid, the thin film, is almost gone, very little, and you only have this boundary layer. Yeah, and unfortunately, by being on this side, the friction is gonna shoot up. And if for whatever reason, the viscosity drop, let's say for whatever reason, because part of the reason why you can go on the left-hand side is that mu in the numerator is small. When mu is small, it's going to the left. And if the viscosity drops, the friction increases. Yeah. And when the friction increases, the temperature will increase, which will drop the viscosity even further. And this is too big of a problem. You know, the difference between water and oil and is viscosity in terms of this lubrication. And we need viscosity. If you lose the viscosity, the fluid will not give you the lubrication that you need. And that's why it's unstable. It's like you drop the viscosity, then the friction increase, then the heat increase, then the viscosity drop even more. And that's why we call it unstable. You got me, Shabab? So what the engineer, basically, the boundary lubrication should be expected for slow speed. So if you have a slow speed, you can depend, as we said, even in other lecture, the last lecture, that about, you know, with the velocity of 10 feet per minute or about 0.05 meter per second, you can handle your situation with boundary. Otherwise, you'll be in trouble. So the question is, what is this value? This value, okay, to keep, say, a design constraint to keep a thick film lubrication is to ensure that this value is greater than this number, which is Nren, okay, revolution per second per PSI, okay, which is equivalent to 30 centipoise RPM per PSI. I think I may have a discrepancies between these values, but I need to double check it, okay? Because this is the same as this, and here we have 0.33, and here we have 1.7. So I need to double check this issue. Now, in the other class, I had to stop at this slide. We have around like 7 minutes more, 6. So it's pretty good that we don't need to proceed further. But this is something that we're going to talk about, inshallah, next class. So I'm going to stop here, okay? So please just give me a second. I need to take your attendance.